Well, hello everyone. Assalamu alaikum. Today I'll be talking about one of the most important aspects in machine learning for researchers, for developers, and basically for everyone who is interested in using AI in their projects, in their studies, etc. So, foundation large language models towards understanding human languages. So, today I'll be talking about a brief story. It is just a storytelling about the foundation large language models such as BERT, GPT, BART, etc. So it's presented by me, Mohamed Berrimi. I am a Google developer expert in machine learning, and I've been working a lot on natural language processing and computer vision. So before I start my talk, I will be just presenting a tweet from Andrei Karpathy, which is a ex-chief AI scientist at Tesla. So he's the person who developed the autopilots in Tesla. Okay, so he's one of the most brilliant AI engineers that ever existed. So he says that the hottest new programming language is English. So what does he mean by that? So he means by that you do not need to learn the programming language from scratch, or you do not need to master it. It's good to master it, but now if you just can use English, you will be able to program and develop everything you can. Another tweet which explained this, he says that Copilot, which is an AI system, is an AI system, it writes 80% of his code. Imagine a chief AI scientist at Tesla, 80% of his code is already written by an AI. So the question is, so this is an example of Copilot. So you just give it a prompt. So this is the prompt. Prompt is basically the input or the intent or your request. So you give it your input and it gives you a code, and it's really awesome. And now it's being used on GitHub and it's paid. Okay, so the question is, how did we get so far? How did we achieve such great performance? How did we? How now we are able to make computers understand our language, generate code, generate music, generate images, generate everything that we want. So how did we come so far? So the presentation today will be just a story about from machine learning based techniques to deep learning techniques to transformers to pre-training large language models. So the, the outline of the presentation is we briefly talking about natural language processing, some of its applications, some of its motivations, some its use cases in feature representation. Then I'll be talking about one of the most important or أهم شيء حدث في deep learning, the most important thing that ever happened in deep learning, which is the transformer model architecture, then large language models and beyond. So it is estimated to have 350 billion emails are sent by day, and 5,000 posts, Facebook posts are posted by day, and almost 500 tweets are tweeted per minute. So we have a very large data which is being generated each day, and we know that this data, we need to understand it, we need to represent it clearly, we need to learn from it. We just cannot throw it like this, but we need to make use of it. But there is a problem. All this data is unstructured and it is generated with different languages. So it's generated with Arabic, English, French, Japanese, Chinese, etc. And it is estimated to have more than 1,000 languages all around the world. So we have a big, we have a very big problem here. So we have large data sets, we have a large unstructured textual data, and we have variety of data. So how can we develop an AI system? How can we simply develop an automatic system that is able to understand this data, learn from this data, and generate data like we are speaking? So natural language processing is actually the answer to this. So understanding the natural language processing is all about understanding how human communicates. So we are going to take this textual data. We are going to train machines to learn and understand how humans are communicating, how to get computers to replicate this behavior, that so that we can interact with computers in more natural manner. So in natural language processing, we have two steps. We have the data and we have the machine learning. But first, the data. If we can, if we can represent the data effectively, it will be easy for any machine learning model or any deep learning model to give good performance. Why is that? So the most significant part in natural language processing is the way you present or you present your input textual data into your machine learning model or into your deep learning model. Why is that? Because words has meaning. Our words have meaning. الكلمات عندها معنى. تختلف الكلمات هذه من context من مفهوم ولا من محتوى إلى آخر. But also the vector representation should also be meaningful. If a word has a meaning, if we are going to represent it as a vector or as a matrix or as a tensor or whatever you want, these vectors should be meaningful. So how can we represent words into a meaningful way? So this is feature representation or text representation. So text representation has evolved تطورت عبر السنين. The very first technique that develops a picture representation or text representation technique, it's called bag of words. So bag of words is basically a very simple thing. So you take a document and you split a document, it could be sentences, for example, and you take these sentences and you split them into tokens. It's called tokenization. And you represent the occurrences or the frequencies of these tokens into these documents. Then you feed just this vector into machine learning model. So this is back of word or TF-IDF, and most of basic or classical vector representation techniques, which are basically consistent of representing the frequency of the words or sequence of words or sequence of characters into a document, and that's it. But there is a big problem into this, which is this vector representation does not encode anything about the contents, about the context, and it does not tell us anything about what we are saying, about the context, about the meaning, etc. So we need better vector representation. So word embeddings. So word embeddings are powerful vector representation techniques that uses neural networks, that uses artificial neural networks. So how is that? So basically, the idea behind word embeddings is uh, we are going to train a neural network. So each word, so each two words that have similar meaning, their vector representation will also have similar vector representation. So for example, if I take a word car and the word vehicle, their meaning are the same, سيارة وسيارة. But also we should their vector representation, if we encode them into a vector space, their vector representation will be similar. Okay, and this is how we can really represent or efficiently represent each word into vectors, but these vectors should also has meanings. So for example, and if we calculate um, the um, cosine similarity between two words, their vector representation will be very small. So it's called we have word to vec, we have glove, we have multiple vector, we have fast text. So all of these are vector representation, are word embedding models. So word embeddings, just to repeat again, word embeddings are all about training a neural network mod, a neural network that represents the words that gives the words that have similar meanings. It will represent them as into vector representation in the vector representation space into similar vector representations. So how we have been doing that? So we take the input sequences, we feed them into a neural network. So we feed them into the word embedding. So here in the very first step, we are going to tokenize the tokens, and then we are going to feed them into the word embedding space. And this word embedding space, it will be just a mapping, because we know the apple, we know the vector, we already know the vector representation of apple, we already know the vector representation of is, etc. So this will be a mapping, okay? And then we feed all these vector representation into an LSTM layer or GRU or one-dimensional convolutional neural networks, etc. And you are going to find, for example, if you are going to do sentiment analysis, we are going to have a sigmoid or a softmax output layer at the end, and we are going to find the sentiment. But unfortunately, these vector representations are limited. Why? So the context of the words is not encoded with the tokens. So Apple here will have vector representation. So the vector representation of Apple, it will be a fixed and unique vector. And it does not change whenever the context of word Apple changes. So for example, Apple is the company and Apple is also the fruit. So for example, if I encode, I ate a fruit, so I ate an apple, so the apple token here in this sentence will be represented as the same vector representation as Apple is a good company. So which is basically wrong. So we need better word embeddings models. So this is the first thing. The second thing is the neural networks that are built, for example, LSTM, bidirectional LSTMs, GRUs, etc. So these RNNs are very slow in training, and they consume a lot of computational resources. So we need faster neural network models, and we need effective word representation models. And we have the transformer architecture. So the transformer architecture is basically the solution to every question we had before 2017. So the transformer architecture is a simple idea, a single idea that changed everything about deep learning. So the researchers by Google, they wrote a paper and it's called Attention is All You Need. What do they mean by that? Is that they are going to drop any recurrencies, we are going to drop any convolutional neural networks, we are or convolution operations. We are just going to use feed-forward networks and attention mechanism. So this actually give the best performance across multiple NLP applications, including machine translation. So, before that, before the arrival of self-attention mechanism, so the attention here is called self-attention mechanism. So before the arrival of self-attention, so we had the attention mechanism. So the classical attention mechanism is basically we are uh, in a sentence, we are going to calculate the attention of each word in the sentence. So, for example, the animal did not cross the street because it was too tired. So, if we are going to take this example, if we are going to take this example, we are going to calculate which word or which words contributes the most in the context, or which word contributes the most in the task. If we are, for example, doing sentiment analysis, but in self-attention, we are going to calculate the weights or the impact of each word on all the other words in the sentence. So we are going to find or calculate the weight of animal on the street, the weight of animal on the because, and the weight of animal on it, and on was, on to, and tired, etc. So we are going to calculate the effect that each word has on all the other on the other sentences in or on the other tokens in the sentence. Okay, so this is self-attention mechanism. So the transformer model architecture is an encoder and decoder neural network, because it was used for machine translation at the beginning. So if we look very clearly, so we have the tokens here of the input sentence, and then we have the multi-head self-attention and feed forward and etc. So it is just head, multi-head attention, normalization, and feed forward, and it is repeated multiple times. The decoder is as the same. So we do not have any LSTM, we don't have any convolutions, we do only have multi-head self-attentions. And by doing that, we have contextual embeddings. So now Apple will have different representation in different sentences. So the vector representation that will be generated using the transformer architecture. So basically here, if we are feeding the inputs into this encoder, so at the end we'll be having the contextual embeddings. So contextual embeddings, by its meaning of the word, is we are going to have vector representation of these words that depends on the context. So Apple here will have different representation in different sentences. Brand will have different representation in different sentences, etc. So each word will be encoded as it is employed in the context. Okay, and of course, the transform architecture is parallelization. It is very fast, and it received best performance across multiple or all NLP classification tasks, including text classification, or including text classification, name entity recognition, machine translation, summarization, etc., and also including language modeling. So, language modeling is all about trying to predict the next sentence we are going to talk. Okay, so the very first, it's not the very first, it's we had before Elmo, but the very first large language model that used the transformer architecture is called BERT. So BERT is a bidirectional encoder representations from transformers. So from this slide on, in هذا slide إلى آخر presentation, we are going to talk only about the transformers. So هذا this is an end this, or this is clear message to everyone who's now attending this talk to go and read more about the transformer architecture, because it is used in all of the papers, in all NLP papers, in all computer vision papers, and it has did a revolution in multiple deep learning applications. So, so what is BERT? So BERT is a bidirectional. So it is bidirectional, as we can see from here. So representation from transformers. So each blue here is the transformer. Okay, and what they do is they did connections from left to right. So they added connections between all the transformer heads from left and from to right to represent the meaning of the word. So, for example, and why they did that is if we read the sentence from right to left, and sometimes we really need to read it from left to right, or we are just going to be to back um, in time to understand more about the context of each word. Okay, so they took the transformer architecture, they trained it into a bidirectional way, and they pre-trained it into a using a large corpus. So I said a word, it is pre-trained. So what is pre-trained? Okay, so we in BERT we have two steps in the pre-training and the fine-tuning. So in the pre-training, we are taking this deep learning model, which is called BERT. We are going to pre-train it on a very, very, very large data set. So what is the size of the data set? It is gigabytes or gigabytes of text scrapped or collected from the internet, for example, from Wikipedia, etc. So the pre-training, what do we mean by the pre-training? So uh, researchers, what they did is that they posed a question. If we can train a large deep learning model on a large corpus of data, and we can force this language model to understand the language, then we can use it for text classification, we can use it for sentiment analysis, we can use it for machine translation, etc. So إذا كان إنسان يفهم اللغة، يفهمها بحذافيرها، يفهم الكلمة اللي حتقولها من بعد، يفهم الكلمة اللي قلتها قبيل، يفهم الكونتكست تاع الكلام، بطبيعة الحال راح يفهم إذا الكلمة هذه أو الجملة هذه راهي سنتمنت تاعها سهلة جيدة أو غير جيدة، إذا كنت تحكم بطريقة ساخرة، إذا كنت إذا يقدر يعرف يدير text classification وحده. So they are going to train using self-supervised learning using this deep learning model. Okay, so this is the pre-training. In the pre-training of BERT, we have two tasks. We have the masked language modeling. So masked language modeling is what they are going to do. They are going to take each sentence in the corpus, and they are going to mask randomly tokens from these sentences. And then they are going to train BERT to predict these random masked words. If, for example, the man who went to the, and then they are going to mask this token, he bought a mask of milk. So in the sentence, in the original corpus, these masks were tokens, okay? But what they did, they masked randomly tokens in each sentence, and they trained BERT to predict those tokens. If the model predicts them correctly, then it is good. If it does not predict them correctly, then we have to train it longer and longer. Okay, so for example, here labels will be tokens, so it is a store or a gallon. So this is how pre-training using masked language modeling. Okay, there is another way to pre-train it using next sentence prediction. So, for example, if we are going to have the man went to the store, he bought a gallon of milk. So it is a next sentence. So another way, another example, the man who went to the store, or penguins are flightless. So these two, sorry, so these two sentences are not correlated, does not have the same meaning. So not sentence, not next sentence. So we are going to pre-train BERT to predict the next sentence. So it understands if it really understands the sentence that we are reading, then it can clearly predict the next sentence in the document. And we are going to see some examples at the end of the presentation. So after pretending this, we are going to fine tune it. So fine tuning is one of most basic examples or aspects or concepts in deep learning. So we are going to have these new vector representations of birds. Uh, just do a mapping. So each word will be mapped into its vector representation, and you are going to have a classifier or any outputs layer that we want to do. Okay. After that, so in the original paper, so in the original birds paper, so they trained it on very large corpus of data. But this large corpus of data was at the beginning English, and then they pre-train it on multilingual corpus. For example, it includes English, Arabic, French, Chinese, or Mandarin, or Spanish, etc. But unfortunately, these multilingual BERT models did not achieve great performance, for example, in Arabic, in other languages. So researchers what they have been doing recently is to pre-train BERT, the same architecture, on a corpus on that specific language. For example, we are going to take BERT and pre-train it on Arabic. And we have AraBERT. We have multiple Arabic-based language models. We have French, we have Camembert, and we have multiple language models. So as we are all talk Arabic, we know that the Derja or the dialect, it differs from a country to another or from a region to another. And we find out that our bird did not get good performance in Algerian dialect. So what we decided to do, so uh, me and Amin Abdawi, and Amin Abdawi, we pre-trained a new large language model. We called it Zuribird on a large Algerian corpus of data. Okay, and I invite everyone to test it if you can talk Algerian or understand Algerian. It is available on Hugging Face Space. Okay, so moving forward, please, if you have any questions related to birds, related to transformers, related to Ziri birds, please don't hesitate to ask any questions. Okay, but there is a battle uh, between how um, how to uh, propose large language models that outperforms each another. So after BERT, the researchers are companies such as Microsoft, OpenAI, Apple, Facebook, etc. So they discovered that if we can pre-train another deep learning model, another deep transformer model on larger data sets, we can have better contextual embeddings or better language models. So there have been a battle. So BERT has 340 million parameters. So at the beginning, and I remember when BERT went to public, it has 340 million parameters. And everyone basically was shocked because it was too large. It was the largest ever existed model in deep learning, in language modeling. And but after that, multiple language models have been produced or have been proposed, including GPT-2, uh, Microsoft Turing NGL, and GPT-3. So GPT-3 has 175 billion parameters. So it is billion. Yes, it's not million. It is 175 billion parameters, and it's really uh, large language model. But the battle did not stop here because last year Last year, Google published another large language model, which called Palm. It has 540 billion parameters. It's almost 5 times larger than GPT-3. But Palm is not yet um opened or to the markets. But today, and while I was presenting this presentation, preparing this presentation, there is a tweet by Sundar Pichai, which is CEO of Google. So so he wrote, "We are excited about Palm API, an easy and safe way for developers to build top of our language models and make suit." So basically, in this tweet, it's just today, March 14th, the next generation for AI developers and Google Workspace. So they made, they are going to make Palm API open for public, which is very interesting. I'm really, I cannot wait to use it. Okay, back to the slides. So the question is how to propose large language models. So it is very good question and very easy to answer. If you have computational resources, for example, TPUs, as the case for Google, or GPUs, as the case for OpenAI, so you can really, if you have computational resources, if you have larger data sets, then you can have larger language model. So it's all about finding larger data sets. It's all about finding um, it's all about having the computational resources to pre-train these large language models. Okay, so GPT-3. Now I'm going to talk just about GPT-3 from now on. So GPT-3 is bit-tree generative pre-trained transformer. Again, the transformer architecture. It was pre-trained on 45 terabytes of text. Imagine that, with a total of 300 billion tokens, consisting of wide range of sources, including books, websites, and other documents. Uh, but OpenAI, after the release of GPT-3, it had very serious problems, which is bias, hate speech generation, offensive context, inappropriate content generation, etc. And it was poor for code generation. It was poor for dialogue or prompts understanding and generation, etc. So what they did is to pre-train or to make GPT-3 safer and better. So GPT 3.5 is a fine-tuned version of GPT-3. The main feature of GPT 3.5 was to eliminate toxic outputs to a certain extent, to eliminate receiving toxic outputs, and also they pre-train it to generate code. So Copilot, for example, is a smaller model of GPT 3.5. But the most important product of GPT 3.5 is ChatGPT. So ChatGPT is scary good. We are not far from dangerously strong AI. So ChatGPT, I'm sure that it does not need any introduction, because everyone know now in these days is, is just talking about ChatGPT. So ChatGPT is a conversational large language model, which is proposed by OpenAI. So it is basically built to it is a dialogue system that is built to answer follow-up questions, admit its mistakes, challenge incorrect premises, and reject inappropriate requests. So for example, if you are going to ask it how to make a gun or how to make a bomb, it will not give you an answer. So the power of GPT-3 or ChatGPT is that it has received. So the power of ChatGPT that it has received 100 million users in only 2 months, and it took 30 months for Instagram to reach 100 million users, etc. So it's very widely opened and widely used almost everyone on Earth. So what is just ChatGPT? So this is just a simple, funny slide. ChatGPT is large language model developed by OpenAI that is trained to generate human-like responses to natural language inputs. So it is so ChatGPT is based on a deep learning architecture called the transformer. So the transformer architecture is basically very important, and you need to learn it as soon as possible. So another use case for ChatGPT is it is listed as the co-author or author or co-author of 200 ebooks on Amazon Kindle. So it's really being used almost everywhere. But the question is how it was pre-trained. So how does it work? So to develop to develop ChatGPT, so OpenAI had to train a large language model to understand human language, and to understand human language, they used GPT-3 or GPT 3.5. Then ChatGPT is a dialogue conversational AI language model. So this human language model, language model should understand dialogue, uh, dialogue and how to interact with the humans. And so to do that, they pre-trained or fine-tuned GPT-3 into dialogue data, which is called the instruct GPT. So it takes instructions from the users, and based on those instructions, it's going to response response to these instructions. So it's called instruct GPT. Then improve dialogue generation by reinforcement learning from human feedback. So this is a snippet taken from OpenAI website. So we are going to pre-train. So how to? So this is just a snippet from OpenAI website to answer or to explain the improved dialogue generation. So to improve dialogue generation, what they did, so they for multiple prompts answers, so they hired labelers or human labelers to prompts and several so we have a prompt and several model outputs are sampled, and for each labeler it will be they will rank each output, is it good, bad, or inappropriate. And this based on these labels from the labelers, they are going to fine tune the large instruct GPT into this labeling. Then it will learn how to really understand how to grade or how to better dialogue generation. Sorry. So this is another snippet to explain it. So it just have an prompt, and of each prompt we have multiple dialogues that are generated from each prompt. So you are going to hire labelers to label these generated dialogues. Is it good? Is it bad? Which is one is good? Which is one is better, etc. And we are going to take this labeled dialogues and fine-tune GPT-3 to understand which dialogue is good, which dialogue is worse, and how to improve dialogue generation. And and this is called reinforcement learning from human feedback. And by doing that, ChatGPT can really uh, generate great dialogues. Okay. So some limitations and perspectives of ChatGPT. So efficiency. So some of the context generated by ChatGPT is incorrect, but ChatGPT is quietly confident about these responses, but it is incorrect and you cannot really trust it. Adaptability. So, if an information that's just ChatGPT is limited to 2021. So the data that is pre-trained on ChatGPT is only back to 2021. And if an information that is has been updated from 21, for example, that has been already updated in 2023, uh, ChatGPT do not know it because it is very limited. Trustworthy. So what do we mean by trustworthy is ChatGPT does not really cite its references or its resources, and it's one of the most um, weaknesses or limitations of ChatGPT because it gives you output or it gives you information, but it does not gives you references from what it got those answers. Limited knowledge, as I explained, it is only has knowledge up to 2021, but after 2021, it does not has uh, further language knowledge. It's far from human level intelligence, which is basically obvious. So Jan LeCun is one of the pioneers in AI and deep learning. So it is he says that uh, uh, ChatGPT is far from human level intelligence. So this is another paper that shows the mathematical capabilities of ChatGPT. Uh, so, uh, so it's just a group of researchers from Oxford and from Cambridge, etc. So they took ChatGPT and they tried to evaluate it into multiple mathematical data sets. But the conclusion was, will ChatGPT get you through a university math class? No, you will be better off copying from your average peer because ChatGPT was really bad into these mathematical tests. So it's very limited, yes. Another quotes that I would like to explain. So Yoshua Bengio is the very first AI scientist that proposed neural language models. So an AI system should not learn only from text. It should learn from the same time how the world works. So an AI system is basically should learn from images, should learn from videos, should learn from perception, should learn from text, should learn from a variety of data. So and how to describe the world with language. So ChatGPT is not the case. Jan LeCun, he said that the factual, logical, and physical reasonless mistakes that pure large language models make clearly show that they have not captured much of human thoughts. And Sam Altman, OpenAI CEO, so he's basically the one responsible for developing ChatGPT. So he says that it is a mistake to be relying on ChatGPT for anything important right now. So be free to use ChatGPT, but at your own risks. So thank you for your presence and thank you for your attendance. Thank you for attention. If you have any questions, I would be more than happy to answer them. So if you have any questions, don't hesitate to type them in the comments below. I will be responding to them at any time, or you have my email, or you can reach me on Twitter. Thank you so much, and may we meet again into another course on large language models. So this was just a beginning presentation, and maybe we are going to have a multiple um, event series on using large language models. So thank you so much.